Okay, so it's module 6 time, and this mix is going to be a little bit on the brief side. There's not as many simulations for me to share with you in this particular PowerPoint presentation, so that may be good because you'll probably get through this a lot quicker. It's kind of an awkward module or an awkward chapter. This is chapter 7 in your book. It's about the sun. In a previous version of this book, the sun chapter was actually after the solar system, and the current edition now has the sun before we get into the solar system. So I've kind of set it aside as its own module. There's not a whole lot of content here. So I'm not going to have a big presentation as far as the lecture mix. I do want you to spend a lot of time on the lab activity for this module because it's a little more involved. It's not your regular simulation that you've been dealing with. This is an activity that I wrote a couple of years ago when I did a summer program at the University Corporation for Atmospheric Research in Boulder, Colorado. And it's about sunspots. So I'm going to cut you a little break as far as the content of this mix in hopes that you'll spend a little extra time doing the lab activity this week. Okay, here's some basic factoids about the sun. I'm not a big fan of memorizing facts, but you should be familiar with our sun. Well, why is that? Because it's so darn important. Without the sun, life on Earth would not be possible. I like to think of the sun as being sort of a kindred spirit. I'm just an average middle-aged guy, and the sun turns out to be just an average middle-aged star. It's not the brightest star. It's not the dimmest star. It's just kind of average. It's got a spectral type of G2. Now you're going to learn more about spectral types when we get into chapter 13, so that's still a couple of modules away. But just kind of put that off and tuck that off into the back of your head, that the spectral type is a G2 star. Obviously, it's the brightest thing in our sky. Well, why is that? Not because it's a particularly bright star, but because it is so stinking close. Our sun is only 8.3 light minutes away, remember. So the light that we see when we look out the window left the sun 8.3 minutes ago. Think about the next nearest star, Proxima Centauri, next nearest star to Earth, which is 4.3 light years away. So that tells you how close the sun is, and that is why it appears so bright. So we've already dealt with the apparent visual magnitude. Apparent visual magnitude is like -26. Its absolute visual magnitude is actually a 4.83. And we'll talk about absolute magnitude in a couple of chapters. The sun is obviously very large. It's the largest thing in our solar system. It's 109. You can put the Earth, at least its diameter. Remember the Earth's diameter? It's about 8,000 miles, right? The sun's diameter is about 860,000 miles. So you can actually put the Earth about 100 times across, 110 times across the sun. And of course, volume-wise, it's about 1,000,000 times the volume of the Earth. So you can put about 1,000,000 of the Earths inside the sun. And obviously it's much more massive, but when you take the overall mass divided by the volume of the sun, it is not as dense as the Earth. It's essentially a plasma. It consists of a gas. It's actually a ionized gas called a plasma. So its average density is 1.4 grams per cubic centimeter. Not as dense as the Earth, but not as low density as, say what water is. Water has a density of 1 gram per cubic centimeter. So the sun would sink if placed in a big enough bathtub. Its temperature, well, it ranges quite a bit. Where the energy is produced, which is the core, it's about 15 million Kelvin is the temperature at the core of the sun. When you get to the surface of the sun, which is called the photosphere, its temperature is about 5,800 Kelvin. And that's the temperature that it's compared with compared to other stars. The surface temperature or the photosphere temperature is how we compare our sun to other stars. Again, 5,800 Kelvin is an average temperature for a star. It's not the hottest, it's not the coolest. This sort of goes without saying, but as we talk about the sun, please, 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 please do not look at the sun directly. If you are going to look at the sun, your best bet is to find somebody who has a solar filter. That's probably the safest way, but there's also a way, if you're looking through a telescope, of using what's called a projection technique. And this is a way that I show students in my traditional class. I actually use both techniques, the projection technique and the solar filter technique. And that allows us to look at things like solar sunspots during a solar eclipse. You can use these techniques as well. And but never, of course, look at the sun directly. Okay, this slide is similar to a graph that you see on page 120 of your textbook, essentially just showing the different parts of the sun's atmosphere. Again, there is no solar surface, but essentially what we consider the surface is the photosphere. And then above the photosphere, we consider that the rest of the atmosphere. So what you'll see here is that there are different temperatures at different layers of the atmosphere. So the photosphere is actually the coolest layer of the sun. And then as you move up into the chromosphere, it gets warmer, and then a dramatic warming as you get into the corona. And then you also see an increase in temperature as you then move into the sun. As you move toward the core, there's an increase, because as we know, the core of the sun is upwards of 15 million Kelvin. I include this image mainly just to show that the sun, when viewed in different types of, or by different types of telescopes, can look quite different. So we see a visible image, and we see an ultraviolet image. And we notice that on the visible image, we're seeing mostly the photosphere. In the ultraviolet, we're seeing primarily chromosphere, which is quite interesting. And then, of course, you can also view the corona under visible light and just see different features of different parts of the sun. Your book mentions the topic of helioseismology, which may sound sort of familiar. You may be familiar with the term seismology, which is essentially the use of seismic waves in the Earth to figure out the Earth's interior. We haven't drilled very far into the Earth. We've never explored to the center of the Earth. How do we know about the structure of the Earth? By using either earthquakes and the seismic waves that earthquakes produce, or our actual, we'll set depth charges, set off explosions, and see how the waves travel through the Earth. And that's a way of learning about the structure of the Earth, the different layers and such. Same thing in the sun. You have helioseismology, where we can learn about the sun. We can't see into the sun, but we can study waves that pass through the sun. And vibrations in the sun, and that's an area called helioseismology. One of the more important lessons you should take from Chapter 7 is the difference between nuclear fusion and nuclear fission. Nuclear fusion is when you take light elements, like hydrogen, helium, and smush them together to produce energy. And that's what the sun does. The sun produces energy via nuclear fusion, light elements being combined into slightly heavier elements, and energy is released in the process. Here on Earth, nuclear power plants do the opposite. They use what's called nuclear fission, where you take very large, ungainly kind of elements like uranium and plutonium and allow them to radioactively decay. They break apart and liberate energy in the process. And so that's a fundamental difference in the two different ways of creating energy, nuclear fission versus nuclear fusion. Fusion is small, becoming larger. Fission is large atoms breaking down into smaller. Now, where's the tipping point? Well, it turns out it's on this scale. All elements up to starting from small elements like hydrogen, you wind up getting energy out of fusing those elements together up to a point. Once you get to iron, fusing elements is no longer profitable, in the sense that you can fuse iron or even anything that's larger than iron, lead for example. You can fuse lead. It is possible, but it takes more energy to do it than you get out of the reaction. So it's a losing game. And same thing with fission. Fission kind of works the other way, where when you're splitting really, really large stuff, energy is gained. But you can split helium if you want. You can do nuclear fission on helium or lithium or whatever, but it's going to take more energy to do it than is liberated from the process. So essentially, iron is the end game for both these processes. Nuclear fusion, nuclear fission would both stop at iron in most cases. The fusion that occurs in the sun is described on page 135 of your textbook, and it's called the proton-proton chain. You don't have to get too wrapped up in the minutia of this reaction. The important thing for you to understand is that in the sun, you start out with hydrogen nuclei, which are called protons. You essentially strip away the electron. You have a plasma of hydrogen protons at the center of the sun. We know there's very high temperatures at the center of the sun. We know there's a great amount of density at the center of the sun. Now, these protons are positively charged. You wouldn't expect them to want to be close to each other, but they're so packed, they're moving at such great velocities that occasionally they smack into each other. And you go through a process then of smacking into other products of other collisions until eventually you wind up producing a helium nucleus with 2 protons, 2 neutrons. That's the end product of this chain reaction. You start out with 4 hydrogen protons, you wind up with a helium nucleus. And the important thing to understand is that the total mass of all the ingredients, think about this as being like a cookbook reaction, where you start out with ingredients and you wind up with a product. The mass of the ingredients, those 4 hydrogen protons, total mass is a little bit larger than your end product. The helium doesn't have as much mass as these starting products. So therefore, some mass has somehow been apparently destroyed. Well, it turns out it's not destroyed. It is simply converted into energy according to Einstein's equation, E equals mc squared. Okay, so now that we understand how the sun produces energy at its core, the question is, well, how does that energy get from the core out of the sun and essentially, or eventually, to the Earth? Well, it turns out that it uses 2 processes. Radiation, there's 3 ways of transferring energy. Conduction, like when you put your hand on a hot stove. The stove conducts energy from it to your hand. That's not going on in the solar interior. However, radiation does occur. So we have energy produced via nuclear fusion, and then energy is transported outward through radiation, essentially photons moving outward through essentially the inner 2/3 of the sun. Now this is for a sun-sized star. There are other stars that are different sizes and they have different amounts of radiation, convection going on, sometimes one and not the other. But for the sun, energy is transferred via radiation for about 2/3 of the trip. The outer third of the sun, now we have what's called convection, where that's the transfer of energy via the motion of a fluid. So in this case, it's plasma, ionized gases that can sink and rise. Convection also occurs in your house, where air moves and moves heat energy around your room, or again in a pot of boiling water. Heat energy is transferred via the motion of water, a liquid in that case. But again, we have radiation on the interior of the sun and then convection going on a little closer to the photosphere. I'll be brief in talking about sunspots. You'll be doing a lot of work with sunspots in the lab activity of this module, so suffice it to say that sunspots are spots on the sun. As you will or have discovered, the number of sunspots on the sun is not a constant. It varies. It goes through periods of activity and inactivity, what are called maxima and minima. And if you track that, not only the active periods and the non-active periods, but also the locations of the sunspots, you get a very interesting thing called the Maunder butterfly diagram. If you look over here in this picture, this is actually me posing close to the Maunder butterfly diagram. I did this back a couple of summers ago when I was doing a summer program at the University's Corporation for Atmospheric Research in Boulder, Colorado. They actually have an original version of the Maunder butterfly diagram housed there. Now, the Maunders, husband and wife, worked on the butterfly diagram. They were actually British. The husband died, I believe, back in the 1920s, and the wife lived into the 1940s. I believe she died in 1946. But during World War II, for fear of their documents being destroyed in the Blitz of London, they actually shipped the Maunder butterfly diagram to Boulder, Colorado, where it's been housed ever since to keep it safe during the period of war. I didn't give you the answer to that last quiz question, largely because it's kind of tied into the lab activity this module, so I didn't want to give the farm away. But I will mention in this slide the Maunder minimum. Maunder noted a lot of things about the sunspot cycle, including the fact there was a period in the 17th century where there were very few sunspots, and it correlates with a period of rather cold winters across much of the northern hemisphere, colonial America as well as in Europe. And so that's an interesting climate tie-in. We've never seen a minimum quite this pronounced since, but this certainly did tie in with a cool period here on the Earth. So as you figured out by now, sunspots are related to magnetic activity on the sun. How do we know that? How do we prove it? It's proven by what's called the Zeeman Effect, which is described on page 127 of your textbook. We see a splitting of absorption lines. Here's the absorption lines of the sun. We see a little bit of splitting in the vicinity of sunspots, showing that there is some sort of a magnetic effect going on that corresponds to the location of the sunspot on the sun's photosphere. You may not be familiar with the term dynamo. A dynamo is essentially anytime you have free charges that are in motion. So in the case of the sun is made of plasma. It's got ionized atoms. That means they got the protons that are positive, and you got a bunch of free electrons, and all these things are in motion because the sun is spinning. And that's going to set up, anytime you have charges that are in motion, they create a magnetic field. So it turns out that the sun has a very strong magnetic field due to the motion of all these free charges. It also turns out that it doesn't have a constant magnetic field in strength or in position. And that's partly because of the differential rotation. Unlike the Earth, where the surface is all solid and therefore it all rotates once every 24 hours, the equator of the sun actually rotates a little bit faster than the higher latitudes. As you move toward the pole, the sun tends to spin a little bit slower. And so that differential rotation also makes the sun's magnetic field quite interesting. Now it turns out that these fields can get rather complex over time as things start to loop around. And that's what we see here on this slide, is that over about 11 years, the magnetic field lines get so tangled that they essentially snap. This is what's called the Babcock Model. And this gives an explanation as to why you go through a relatively regular period or regular pattern of activity and inactivity as far as sunspots go. And it's all because and also because of the locations going from different latitudes toward the equator. That's all due to the fact that the magnetic field lines get very tangled over time, about 11 years before they start to snap and reset.